two activities of the work package 1. In the afternoon, two presentations of researchers involved in the work package 3, and then other two presentations of work package 4. However, before start with the presentation, I would like to show a couple of slides in which presenting our computational infrastructure, and in particular our high-performance computing clusters. ENEA has 9 research centers. 6 of them have ICT services, and there are also 3 of them with high-performance computing clusters. These sites are located in Portici, Frascati, and Casaccia.
Non hai condiviso, forse?
Non ho condiviso. Ora condiviso. Okay. The main computing facility at the moment is a Cresco 6 with an overall peak performance of 1.4 petaflop. Is equipped with 454 nodes, each of with Intel Xeon Platinum CPU. And there are also 2 smaller clusters in Frascati and Casaccia. This cluster has a CentOS operating system, LSF as resources manager, and GPFS parallel file system. Recently, 2 new cluster has been made available and are Cresco 7, that is 3 times smaller respect to Cresco 7. It has the same architecture, and there are also another cluster located in Frascati that is called X Cresco with an overall peak performance of 1.9 petaflop. And the difference of this cluster is the architecture, because it's equipped with Power 9 IBM CPU, and each node has 4 NVIDIA Tesla GPUs. The difference with respect to the previous cluster are the operating system. Now is Alma Linux 9.2, and the batch scheduler, Slurm, and the parallel file system, last. And finally, I want to share some information about the new cluster that will be released hopefully at the end, before the end of 2024. This cluster is called Cresco 8 with a 9 petaflop overall peak performance, and will be equipped with almost 800 nodes and about 100,000 cores. Is composed by 3 different partitions: a CPU partition, an high-band memory partition, and a partition with Intel GPUs. So these are our computational facilities, and now I leave the floor to the first speaker, that is Serena Donofrio, with her presentation.
Okay, thank you. Good morning to everyone. I'm sharing the screen. Let me know if everything is okay. So, okay, can you see, can you hear me?
Yes.
Okay, perfect. Okay, so good morning to everyone. Thank you to inviting me to solve today. What I'm going to do today is an introduction to deep learning and to graph neural networks, which are the main ingredient when we approaching materials problem with deep learning tools. So in the first part of this talk, I'm going to introduce the main ideas behind deep learning. So for probably for someone is something trivial, but I would like to well introduce to this kind of topic to everyone, and then I'm going to talk about the graph neural network, so a special and particular kind of tool in the deep learning world. Okay, so what is deep learning? What are we talking about, and why is so famous and popular in this moment? Now we are in the machine learning field, and we are talking about that kind of algorithm which want to mimic the human brain, and the idea is that they want to, let's say, learn something from a big amount of data. These kind of structures are called neural networks, and they are composed by neurons and neurons. So these dots, which are called neurons, organized in several layers. From the first one, which is the input one, the red one that you can see in this picture, to the last one, the output one, the green one in this picture. And then there are some hidden layers in the middle, which are composing this structure and are giving the name of deep, since we are going deep in the features of the input data, and we are trying to understand deeply what's happening, something like that. So this is the idea behind just to justify the name. And the idea behind deep learning is behind neural network is that this algorithm learns from data. So our data-driven algorithm and can process several kinds of data, like images, words, graphs, or well, several kinds of data. Of course, we must organize this kind of data in order to be able to give to the network something. So we have to embed the data to a special vector, which is something which can be processed by the deep learning tools. Now, why deep learning is so popular in this moment? Since actually in the last decades, the big data arrived, let's say, in our world, so became available in our world, and then of course there is also a big increase of computational power, which allows this to use this structure, which are really heavy from the computational point of view. So the ENEA infrastructure is really important from this point of view, since it's quite difficult to use this structure on a normal PC. So in our case, we tried. Well, we used the HPC structure that we have in ENEA. So okay. This is something general about deep learning, but today we are going to talk about we're focusing on supervised learning. So what is supervised learning and what are we talking about? Supervised learning is something that happens when our data set, so our amount of data is labeled. What does it mean that is labeled? It means that we have the we have in this picture both the input data, which is going in the input layer, and also the output one. So the one that we want to obtain, let's say, that we want to mimic. So is a label data set. We have both input and output in our data set. And when we have this kind of data set, so we have, let's say that our input guy is not a single element, but is a couple. So is the input and the output, is the input and the output that we want to obtain. So the idea is that these kind of models are divided in the 3 phases. The first one is the training one. So the model is fed with the training set, which is a subset of the big data set that is available. Normally is the 80% of the data. And then the goal is to minimize the difference between what the prediction, so what the model will produce, and the label, that is the real output that we want to mimic. And this process is done with an iteration, and then we try to minimize this difference. We go back and we try to adjust the ways that I'm going to explain you in a few moments what they are, with the backpropagation and the optimization. So we iterate this phase several times, and in this way the neural network is learning which is the perfect prediction for the input data. After this, we have for every epoch, so for every, let's say, part of this iteration, we perform the evaluation to see if the model is going in the, let's say, in the right direction, and for do this, the model is processing a subset of the data set, 10% in this case usually. Then of course we can split the data set in every way we like, but usually the data set is split as 80% training set, 10 validation, and 10 testing. So the data set is validated on a subset of the model is validated on a subset of the data set to see if the learning is going in the right direction. And then at the end of the day, after the training, we test the model to check the final performances and on the test set, and we use several metrics to see if actually the model is learning something, well, is performing in the way that we like. So this is the idea behind the structure, let's say. But how we can link this kind of phase to the first image that I show you with the several nodes and let's say edges between nodes. So what does it mean? Well, let's see just a simple example of a neural network, just to be sure that we are understanding in the right direction. So the simplest neural network that we can think is the perceptron. So the perceptron is the neural network with only one neuron. We can see here in this picture at the beginning here on the left, and we have the input data, which is the x1 and x2, and we also have the label, since we are in the supervised world, which is y prime. So it's not here in the picture, but we have y prime, which is our label. So the input data is not just the x vector, so x1, x2, but is also the label corresponding to that vector. So we have this input, which is x1, x2 in a couple, since it's the vector which is going in the input layer, and then we have y prime, which is the label that we want to obtain, that we want to mimic in some way. Then what's happening? It's happening that we have only one neuron, and who are the people the main character of this perceptron. So we have y prime and y2 that are something on these edges, which are called weights. The weights, you can think about them just as parameters. So it's something that can be modified during the time. At the beginning, usually, well, depends of which kind of training you're doing, but usually we have something which is a random initialization of the weights. So these are two, let's say, two numbers. Who cares about them? It's something at the beginning, but has been seen in the well, has been studied and proved that actually is more well, is better actually to start from not just from random weights, but from weights coming from another train, also for another kind of task. We don't care about it, but actually starting from something is better than starting from starting randomly. So, okay, we have the weights, and then we want to, we have this B here, which is the bias, which can be added or not. Then we can sum this stuff, and then we apply F, which is the activation function, so something which delinearizes the process and also control the output in a special range. There are several activation functions. Well, but of course we have a set of famous one which are used during during a standard neural network approach. So at the end, what's happening here? So who is this W, this Y? This Y is actually the output, and the output is, oh, here I forgot the B, but anyway, is the activation function applied to what? To the product between X1 and this weight, X2 and this weight, sum together. Then we have to add the bias here. I forgot it, sorry. We sum everything together and we apply our activation function F. So this guy here is our prediction, is our Y. Now the question is, okay, but is this Y close to the Y prime, so to the label that we want to obtain? And if not, what can we do to be able to well, actually, ideally we want that that Y coincides with Y prime, but the idea is, okay, let's compute the loss function. So a difference, a metric which allows us to compute the difference between these two guys. So we perform this loss function. We see if this distance is, how much is this difference, and then we try to minimize this difference. Doing what? Going back in our process and adjusting the weights W1 and W2 in order to get that Y is as close as possible to Y prime. So this is the idea behind the let's say a simple neural network with just one neuron. Of course, this stuff can become more complicated, and of course, adding more neurons in the middle, more layers, and then you can see here on the bottom that when we think about this stuff with a bit more with more neurons, what's happening is just that we are performing matrix multiplication, adding the bias is another vector. So actually, at the end of the day, what are we doing is multiplying vectors and matrices to obtain this output, which can be, of course, much more complicated than the one that we see here with the perceptron. And this is, let's say, a plain neural network in some way, since actually we can add several layers before the dense one, which is the one with the neurons and the connection between neurons that here you can see with the green and red neurons in this image in the bottom right. But you can add several stuff before in order to process the image and to understand if there is another way to adjust the weights and to have something which allows both to understand better the feature of the image of the data, and also allows us to minimize better and better the loss function. So This is just an overview, let's say, to understand which is the idea behind. Of course, with neural networks, we can perform several kind of tasks. So we can perform in the supervised world, let's say the most common are the classification. So we have a few data and we want to understand if they are in a certain class or in another one, or also prediction, of course, since also the prediction is something really is something really used in the classification in the supervised world. But what we want to see, let's say, more precisely is what's happening when our input data is a graph. So what is a graph? A graph is a structure composed by nodes and edges. So something like this in the picture. We have the nodes, which are, let's say, the dots, and then we have the edges, which are the connection between the dots. Why we're interested in graphs? Since actually graph is a structure which allows to represent several kind of data, which usually, which cannot be represented with a simple image or just with not a line of text. Also, a line of text can be, let's say, understanding from a graph point of view. But there are several kind of data that are naturally graphs. So usually to represent a graph in a matricial way, what we define is the adjacency, matrix, which is the one like this that you can see here. So with this, in these graphs, which have red nodes, you can see that the matrix which represent the graph is the one where Aij is 1 when the nodes I and J are connected, and 0 else. You can see the first one, for example, the node 4 is connected to 1, 2, and 3, but 1, 2, and 3 are not connected between them. So we have so if we just check the matrix, you can see that the node 1, actually here in this matrix, we don't have the self loop. So every node is not connected to itself, which is something that you can choose or not to add when you represent the graph. But anyway, we have 0 on the diagonal since no one is connected to itself. And then we have 0 when the two nodes, so for example, here in position 1, 2, the node 1 and the node 2 are not connected, so we have a 0. And then in position 1, 4, for example, node 1 and 4 are connected, so we have a 1. Now, this is a natural way to represent molecules. So this is the reason why we want to use the graph neural networks in the materials world. Since to represent molecules, we just want to say that an atom is a node and every chemical bond is an edge, and that's it. In this way, we are able to represent a molecule without losing any kind of information. Since in this way, this is an abstract way to see this data. And what's happening when we have this kind of data? How can we put this kind of data inside a neural network? Well, we introduce the graph neural networks, which are the neural networks able to deal with graph data type. What does it mean? Well, okay. First thing to do is that the graph neural network has, in general, has this kind of structure. What does it mean? It means that in the first part, which is the one including, let's say, starting from the graph and arriving to the transformed graph, is the message passing part, let's say, when we have a transformation inside the input data. And then after that, we are able to we embed the graph in a vector or matrix, and we are able to feed a neural network with this data. So we're able to represent this kind of data to vector matrix, and then we have the second part. In this case, we have a classification layer and then the prediction, but anyway, we can add whatever we like from the neural network world. But the main question is, how can we start from the input graph and obtain the transformed graph? So what does it mean? And what does it mean, and what's happening? Since actually, when you represent a graph, you know that node A is connected to node B, but then you don't know what's happening about the other nodes. Well, the idea is that every node knows itself and doesn't know the context where it is. And so the idea behind the first part of the graph neural network is passing the message through the graph. So every node must knowing what's happening to the other nodes and who is linked to who. This is the idea. So, and how a graph neural network perform this passage of information, and how, well, so how we start from one graph to arrive to the transformed one, so from layer n to layer n+1. So how does it work, and what's happening in the end? So we are working from the graph level, and the message passing we take, well, since something that I have to say is that we see this graph in this way. So here we see the graph in this way, but on every node, of course, we have features of the node. So we have a set of information which are describing in some way the node. So we have the kind of atom, the mass of the atom, the, I don't know, several information about the node itself. And also the connection between nodes can have a set of features. So which kind of bond is that? How long is that? All this kind of stuff. This kind of stuff are called, are feature of the node or of the edge. So what's happening when we want to perform the message passing? So we take the node of okay, we start from a source node, here the full one in the picture, and we take his feature, and then we check the features of the node which are the neighbors of the source node. So in this case, these two nodes which are connected to the full one. And the idea is that we want to pass the information of the neighbor to the source node. This is the idea. What's happening from the let's say mathematical, well, just written in a formula way. Here is a bit simplified, so this kind of process can be complicated as, let's say, we have a freedom of complicate everything. But the idea is that we start from the node E, we check his neighbors J, and then we compute what? Let's say we can just compute a simple multiplication. So we say that xj, which is the feature vector of node J, can be multiplied by a matrix wj, where wj is a weight matrix. So it's something that we like, since a weight matrix is a matrix composed by parameters. So we can go back and modify these weights if we want. And of course, here we just computed the multiplication, but we can do something much more complicated, and F can be a general neural network. So, okay, we have multiplied, and now we want to aggregate this information together, since we want to pass the information to the source node in the next layer. But to aggregate the information, we need to use an operation which is a permutation invariant. That means that doesn't care, well, this operation doesn't care about the position of the nodes. So, and so we aggregate the f of xj, so the transformation that we had, we aggregate them together. And now here we have some example of operation that we can use. And then we are ready to update the source node, which is at the beginning, which at the beginning we take to select the neighbors. So we aggregate, we did the aggregation, and now we are ready to pass everything. We are ready to pass everything, and we want to update the source node from with the information arriving from itself and the neighbors. The operation is this one is is not so nice, but the idea is that we can add whatever. Well, we add several operations in order to since the idea is that this kind of aggregation can be a small neural network itself. So we have actually an activation function at the beginning, since we want to delinearize and having a controlled how is called a controlled range. And so we start from let's say from layer 0, and then for H0 I, so the feature vector of the node I in the first graph is xi. And then in the layer n+1, what we have is that we have the feature vector of the node in layer n, which is this HIN multiplied by is WI, which is always a Weyl matrix. And then we have the aggregation. So here the agg is the generic aggregation operation, since we can have sum, min, max, min, so several operations. So we have the aggregation one, which is applied to what? To the feature vectors of the neighbors multiplied by the weights. Of course, here we here I wrote a sum, but this operation also can be modified in several ways. So the idea is that we passed from we passed to the source node, so the full one in the first picture, but also in the second picture, so also in the second graph, you see that is the same node, and we update this node with the information about itself and its neighbor, opportunely modified and modified. So now in this way, we pass from the initial graph to the transformed graph, and this operation usually is performed, let's say, less than, the number of layers is less than equal than 4 usually. Well, this is proved in literature. Okay, but now what can we perform after that? Here in the picture that you see, there is a classification layer after, but actually, depends of what we want to do. Since if we want to work from the graph level, after that we have the HN, which are the feature of every node after the transformation. We can perform a graph classification, graph denoising, graph prediction, so keeping the graph all together as we are doing, for example, in the case of materials with Marco. If we want to work from edge level, we start from the two representation of two different nodes, and then we see if there is, for example, a link prediction. Yes, so a link prediction between nodes. And then when we want to work from node levels, there is, for example, classification or clustering of nodes. Of course, edge levels and node levels are not, let's say, I think they are not working from the material point of view, and graph level is the one that we're interested in this, let's say, in our case. But the freedom is a lot. And then last slide, just to say how does it work, for example, when we do a classification of a full graph. So we have our HN, which is the representation for every node, and then we stack them together. And actually we represent the graph. After the graph, we can perform something, as we said before. So with, for example, a multi-layer perceptron, which is just a perceptron with more nodes, in order to obtain, to deal with the classification or prediction, and with the backpropagation, we go back, we update the nodes, and we try to minimize the loss function. So as before. Okay, I think more or less in time, and that's it. Thank you to everyone.
Thank you, Serena, for your very interesting presentation. And now we'll open the floor for questions. Okay, so let's turn the floor to Francesco Buonocore. Will talk to us about ab initio approach in the field of batteries.
Thank you, Simone. Can you see the screen?
Yes.
Okay.
So the floor is yours.
Thank you very much, Simone. So now I would like to connect to Serena's lecture. I see in this talk we talk a lot about ab initio calculation. Why we need ab initio calculation? How are they connected to the neural network? You see that a convolutional graph neural network needs to be trained. Needs training. The training for the subject of our research in mission innovation has been done with data generated by ab initio calculations. The data are available by databases available on the web, or they can be generated by us. Anyway, the training has been done with data from materials project. So
we still see the first slide. I don't know if
no, not moving. It's just
okay.
It is just my introduction. Thank you, Simone.
Sorry.
No worry. So in this in this talk, I would like to explain why we do research on the cathode materials for electrochemical energy storage. And then I would like to give you a flash introduction to the approach we used in theory part of this project. So this is the outline. I'll start by introducing the material discovery for batteries challenge. Then I'll show you the structure, the crystal structure of the layered cathode materials for sodium-ion batteries. And I give you a flash introduction to the approach, to the theoretical approach to model the cathode materials. That is an ab initio approach or first principles. And then I conclude by giving you a presentation of the digital platform for the materials discovery. So, how lithium batteries work? The most of the batteries we use are based on lithium. The mechanism is quite simple to see. We apply a different voltage to the batteries, and we are in charge phase. Due to the electric field, the electrons are moving from cathode to the anode. But we need to compensate the charge that has moved To do this, lithium atoms is moving from cathode to the anode through the electrolyte. This is an electrochemical reaction with the positive change of the Gibbs free energy. So it needs energy from the external of the system to proceed. And so on. The other lithium atoms are moving from cathode to anode until the battery is charged. In the discharge process, we load something to the batteries. In the discharge phase. In the discharge phase, lithium are moving from anode to the cathode spontaneously. This is a spontaneous reaction because it has negative Gibbs free energy. And so, to compensate the positive charge of the ion, one electron is moving from the anode to the cathode, and so on during the charge process. We can have several cycles of charge and discharge. The lithium are moving because between cathode and anode, like in a rocking chair. This is why this mechanism is called the rocking chair mechanism. You see here, for example, that more used materials for the cathode are lithium cobalt or lithium manganese oxide. Anyway, we like to substitute the lithium with another ion. In this application, we would like to use sodium ions and not lithium. Why? Why to do this? Because sodium ion batteries can have several advantages with respect to other technologies like lithium or nickel cadmium batteries. First thing, the sodium is very abundant in the nature. It's more abundance of sodium. So it is available worldwide. While lithium is and nickel and cadmium are limited, have limited availability. So this to use sodium keeps the batteries less subject to the national and international crisis with change of the prices, for example, and the availability. So sodium is not toxic, and it's possible to realize batteries that require a minor amount of critical raw materials. This is the purpose of the new materials discovery. We search new materials for our application for several reasons. The 70% of the total cost of the batteries comes from the materials. So it's good to substitute materials with less expensive ones. So we would like to lower the amount of critical raw materials required. We would like to discover new materials to enable new technologies that are more convenient for some reason. For example, sodium-ion batteries in our case. How to do this research? You can do this research by means of very expensive high-throughput experiments or by theoretical research. We use computational material science to accelerate the screening of new materials. Then I introduce the layer cathode materials. This is a typical structure of layered oxide cathode materials based on transition metals. The structure is as layers, as the name said. We have a layer of transition metals covalently bound to oxygen, alternated to sodium layers. They are intercalated between the layers. So in the charge-discharge mechanism, the sodium ions are intercalated and intercalated. Here show two typical structure of crystal structure. The prismatic two symmetry and the octahedral three symmetry. The number 2 and 3 refers to the number of layers present in the unit cell. So for prismatic two crystal, just 2 layers per unit cell. They are prismatic or octahedral depending on where the sodium is located. It can be in the octahedral side and in the O symmetry, or in the prismatic side. During the variation of the sodium fraction intercalated in the oxide, the phase can change. Within the two phase transition we see here from P3 to O3 and from P2 to O2, we prefer the P2 to O2 transition because this transition allows the lattice do not distort. The problem in the fast transition P3 to O3 that it requires to distort the crystal. This results in a damage for the cathode materials. So you can do several cycles of charge discharge because you damage the cathode. So we prefer the P2 phase. So the challenge of our research is to stabilize, to find the crystal with the most stable P2 phase. In this plot from review, we see different cathode materials with different compositions. The typical formula of the layered oxide sodium ion cathode materials is a fraction of sodium, one or more transition metals, and oxygen. When you put here in this formula just one transition metal, for example manganese, you have a single metal oxide, and in this plot you see that we see the performance of different materials we choose. For example, the black dots are the single metal oxides. And for example, when you insert manganese, you are here. The region of this plot where we like to start, the one with high average voltage and high capacity. So this is the region we like to stay. To reach this region, we need ternary and multi-metals oxide in this case. This is just a selection possibility, but we like to screen all the possible materials. This is impossible to do experimentally, but computationally the story can be different. So we need to explore a broad range of elemental or combination of elements. So we have different candidate compositions, and we need to predict the optimal crystal structure for high performance cathodes. This is the purpose of this research. So we need an approach. We see that finally the approach will be based on neural network, as we see in the next talk by Marco Catillo. This is all the context of our research, but I'd like to give you also a fresh introduction to the ab initio modeling. So this is a theory part. I hope this is not boring. Anyway, I introduce. You see a lot. We see that ab initio calculation is used. Are widely used in the research for materials. But the theory in general, the theory is never been well explained. So I would like to give you a look of the approach. The general approach for a many electron, a many body system is based on the Schrödinger equation. So you have a system, can be a molecule, or a solid here, composed by nuclei in black and electrons. You should solve the many-body Schrödinger equation to find the energy of the system, the total energy of the system. So from the total energy, we have all the properties. You calculate the wave function, the total energy, and you have the full description of your system, your crystal, for example. But to solve this equation is a real challenge. In this example, I don't go deep inside. Anyway, if you want to solve this equation by the variational approach, you would need 10 power to 150 parameters. This problem is unaffordable. It's not possible to solve this the many-body equations, the many-body Schrödinger equations for a system with 100 electrons. It's not possible. So we have to choose other approaches. And the approach I propose you today is density functional theory. In the density functional theory is demonstrated that your many-body problem with interacting electrons is exactly equivalent to another problem easier to be solved. The other problem is the one of a fixed system of non-interacting electrons. For this system, you can write the Cron-Sham-Hamiltonian that gives you a set of independent particle Schrödinger equations that can be solved numerically. This set equation is called the Cron-Sham equation. This is the shape of one of these equations. For every I here, we have one equation. I can be the number, can be from 1 to n, where n is the number of electrons in your system. In this equation, we have the single particle orbitals that must be optimized for the density of electrons, and we have the eigenvalues that are seen as Lagrange coefficients. In this equation, we see that you substitute the many-body interacting potential with single electron potentials, single electron effective potential, where we have the nuclei potential, the electrostatic energy potential, plus another term that is the exchange correlation term. We can do this because we do not define anymore the problem in terms of wave function depending on the number of coordinates of your system, but we solve the problem in terms of the charge density. Charge density, the electron charge density that is defined, that can be calculated by this equation from the fixed orbitals of the Cron-Sham equation. The problem is solved by minimizing the ground state energy of the system, calculated in terms of the potentials and eigenvalues and exchange correlation. This is an exact formulation of the problem of your systems. So in line of principles, the solution is exact. Anyway, the problem is that the exchange correlation potential has not exact form. So we have to choose different level of approximation with different accuracy. More is the accuracy, and more is the computational cost of your problem. Just to see that the exchange correlation is just a little part of the total energy. Here we see in this plot for the manganese the total energy, the kinetic energy, the electrostatic energy of covalent and valence bands electrons, And here you have the exact and here you have the exact exchange energy, and then you have the correlation energies. You cannot see here because it's very small. Anyway, the correlation energy is probably the most important part of the shading of the Kohn-Sham equations to explain how the matter is to explain the cohesion of the matter. Without this term we cannot explain. It's more correlation energy is a small term, but you cannot understand the nature, the existence of materials without the correlation term. And it's very small, but it's crucial. So it's very important to adopt a good approximation for this term. It's very important. Anyway, the Kohn-Sham equation are solved by a self-consistent iterative procedure. I don't go deep inside on this. Anyway, you start from initial guess for the charge density. You solve the Kohn-Sham equation. You don't solve. You put your test charge density into the equation. You obtain a new electron charge density. And you then compare the final charge density to the initial guess. If they are the same within a certain threshold, we have completed your self-consistent procedure. The problem is solved, and then you can calculate energy and the forces. This is how our numerical codes solve the Kohn-Sham equations. In this nice slide, you see a visualization of the Professor John Perdue's point of view of the different accuracy of adopted in density functional theory. It is seen as the step, a ladder from the Bible. For a step of the Bible, Jabok's dream at Bethel, where there is a ladder starting from earth and reaching the heaven. So what's the earth and what's the heaven? The earth is the earth approximations, where there is no exchange, no correlation. So it's is a not perfect equation that cannot explain the matter. The heaven is the chemical accuracy, where you have an exact description of the materials and molecules and so on. Every step of this ladder is a different level of approximation. So the first step is the local density approximation, where the density of charge is approximated with an homogeneous gas of electrons. Next step is the general gradient approximation, where you introduce a dependence of the charge density on the gradient. So the next step is the meta GG approximation, where you introduce also dependence on the kinetic energy. And a very good approximation is the one with the hybrid functional, where you calculate from the orbital the exact exchange, and you include a fraction of the correlations. But this approach is very expensive. And then you have the computational chemistry approaches that are very expensive and not very suitable for condensed matters. For cathode materials, we adopt the following approach. We adopt the general gradient approximations, that is not quite satisfactory. Then you adopt, we can introduce a Hubbard corrections, and then you can use the hybrid functionals that are very expensive. Anyway, for smaller system, for smaller crystal with something like 30, 40 atoms, so you can afford this kind of calculations. In the middle, we have also the symmetry backing. really, when we model your system with a large supercell, you allow the system to relax, you can find the symmetry breaking that allow you to reach more stable geometries. In our approach, we combine the symmetry breaking approach with the Hubbard correction approach. Something more about the Hubbard approach. Really, transition metal have strong interacting D and F electrons, D and F electrons that occupy the D and F shares of the electronic structure of the atoms. They are strongly interacting, and they have a strong correlation that the density functional theory alone is not able to describe. So we need to go beyond the DFT by introducing these corrections, where this correction takes into account the strength of the on-site interactions. This is done by introducing EU parameters. EU parameters that can be calculated by ab initio approaches via linear response method or by experiments. But anyway, we prefer the first approach. So we calculated the U for some systems that we used then for our for the other crystals we modeled in our theory. And anyway, all the crystals not well described by the FT, but they are predicted as metals, but really they are insulators, are called most insulators. So the most we are quite unlucky, because most of the system we are in test for cathode materials are most insulators. So we need this correction to the theory. We use the quantum express code that adopts the plane waves basis set. And when we use the plane basis, when we use the plane waves basis set, we need to use the pseudo-potentials method that address the following issue. The issue is that close to the core of the atoms, we have strong oscillations of the potential of the wave functions of the system. So we need to substitute in the core region the potential with pseudo potential with a smooth behavior close to the core, but exactly reproduce the potential the electron potential in the valence region. So we adopt the pseudo potential when they use plane waves basis set in density functional theory. And this is not a bad approximation. It's a very good description of your system. It is solve probably a numerical problem of density functional theory, because when you solve this problem with your calculator, this oscillation are residues problem. That is the issue is addressed by adopting the pseudo potentials. If you are interested you may be interested to see how is the structure of the input file of quantum espresso, or how the submission to a supercluster like CRISCO-6 is done. If you are interested to see more, you are invited to visit this web page with some tutorial. For example, this is a tutorial applied to the graphene. That is a two-dimensional crystal. So, what we do with density functional theory is to calculate the redox integration potentials. This is done by the total energy of different crystals, and we are interested to calculate the formation energy. The formation energy tell you how much is stable your system compared to the elements in the pure state, when they are in the pure, more stable state. So the calculation formation energy tell us how stable is your system. So we look for systems with very low formation energy, and the redox potential is something that we require to be higher than 3 electron volt for our applications. So we defined an ab initio protocol for our calculations. These are the typical crystals that we used to screen the crystals with our graph neural network. And this is a manganese oxide with intercalated sodium ions. We explore all the possible configurations by substituting nickel and titanium to manganese, searching for the most stable system, as I told you several times. So we defined this protocol for our workflow. And in next presentation, Marco will tell us more about this. This is some example for some crystal we have selected. This is a crystal with 24 atoms. We calculated the band structure, the density state, and so the formation energy and the redox potential when we have the manganese oxide crystal. When we substitute, for example, nickel to manganese in these configurations, we have a new bands that results from the nickels, and we have a new formation energy. In this case, the system is less stable. We have a new intercalation potential, and then we substitute also 1 titanium atoms. In this case, we have titanium bands, and finally we found that when we substitute titanium, the system is more stable. Anyway, this is just a limited selections of crystals. We would like to explore more and more crystals. It's not sufficient to study 3 crystals to say this is the most stable crystal that exists. So for this reason, we have developed the digital platform for materials discovery, where we have workflow of calculation run through the AIDA framework. They are quantum espresso calculation, quantum espresso initial calculation. We developed an artificial intelligent infrastructure based on graph neural network, exploiting CUDA library. All this infrastructure is developed in the Python framework. All the data is readable, is written, is stored and readable in the MongoDB database. All this is developed in the Cresco in the Cresco grid infrastructure. And in the typical workflow, we start from a primitive cell, for example, manganese oxide with sodium atom intercalated. We build a supercell and we optimize this supercell, and we do all the possible substitution in a random way to evaluate the formation energy and the intercalation potentials by using AIDA and quantum espresso. For every structure, we perform a relax calculation. We hold this data within the MongoDB database. We performed more than 1,000 calculations. 70% are successful. Typical run is on 12 nodes for a total of 576 cores, and the typical run requires from 3 to 12 hours and more. So each run is very expensive. we completed computation of over more than 765 crystals, and it's very, very expensive. It's very computational expensive. All the data is available on IEMAP ENEA.it website. And this is the infrastructure, the computational infrastructure that Simone talked about in the introductions. And the conclusion, I finished here. I take 5 minutes more, not so much. My conclusion is that the definition of accurate protocol to calculate ab initio properties of manganese oxide crystals based on sodium ions, also doped derivatives, allowed to generate the database that has been used to test the convolutional graph neural network predictive algorithms. And we see that is very, from the computational point of view, is very time saving. If you are interested to understand more about the FT and the FT plus U, this is some literature you can explore if you are really interested. I thank you very much for your kind attention.
Thank you, Francesco, for your very instructive presentation. So, does anyone have any questions? Yes, Gabriele.
Yes, thank you for your talk. Very interesting. I have a curiosity. When you do these high throughput ab initio simulations, basically you substitute the transition metal in the compound. And so you assume that all the compounds will have that layered structure of the initial compound that was, I think, manganese, sodium, oxygen. So you assume that the structure will be the same and you just substitute the transition metal. Is that correct?
Yeah, it's correct. I should go back. Yeah, this is the procedure. Yes, you assume that the crystal has the same structure. You don't have phase transition. You just examine this case. Yes, indeed, it's this way. Yes.
And do you know how true is it? I mean, do you know whether, excuse me, substituting, I mean, do you have some examples in which you substitute the transition metal and the structure stays the same or changes?
Really, in Spain is found that some of these crystals have the same structure, other one have a different structure. Anyway, we are looking for the most stable system. So I suppose that it's stable enough. It is stable enough to keep this structure. Probably the less stable system do not keep the same structure. But we are looking for the most stable systems having this structure.
Okay.
That is the preferred one because it allows to intercalate and deintercalate sodium without distortion during the cycles of charge and discharge.
Okay, clear. Thank you.
Thank you.
Okay, so let's go on with the Marco Catillo presentation, in which he presents a different approach in the same field, the field of battery. So Marco, the floor is yours.
Thank you, Simone. So can you hear me and see the slides in full screen?
Yes.
Okay, perfect. So today, I'm going to talk about, thank you for the introduction and for making me speaking here. So today we'll talk about an overview and application of the GeoCGNN neural networks on batteries. I'll try to be kind in some parts pedagogical, some parts technical, because I didn't know before about what would be the audience today. So I will mostly talk about this kind of neural network here. So this GeoCGNN, which we use in our project in the machine learning part, our project of IEMAP, or IEMAP in Italian. So let's go to the outline of the talk. So I will first talk about GeoCGNNs for materials. So you already heard about the GeoCGNNs in the talk of Serena before. So I'm going to talk just briefly on this. Then we move to the GeoCGNN, and in this case we go on the details of this kind of neural network that we use. Then we'll go to the application on batteries. In a sense, on batteries, in a sense, we want to, with this neural network, predict properties which can be good for properties of materials for having basically good batteries. I will talk about later. And then we go on the performances on Cresco. Cresco HPC are basically the infrastructure in which all this kind of training and studies are done. So it's nice to talk about this. And then we go to the conclusions and outlook, so things which still need to improve, basically. So GeoCGNNs for materials. Now, in the literature, there are many kind of graph neural networks which are applied on materials. So here there are just, I chose some papers on this, in which there are many implementations. So the one which concerned crystals are the one in this green box. And in particular, is particularly important this GeoCGNN, so Crystal Graph Convolution Neural Network. This is something which our GeoCGNN take inspiration and then improve from this. There are also a lot of kind of graph neural networks in general applied to materials, not just crystals. And particularly important is this message passing neural network. So Serena already told us about what is message passing. And this is also something introduced in our GeoCGNN. And particularly important also is this FISNet, which is used by this GeoCGNN to put also some physical information on our graphs. So as Serena told us before, so when you have a material you want to translate into a graph, but if you have also some hints of the physical information of your crystal, then you can get some improvements on your network. And this kind of neural network has been implemented by a Chinese group, and here's the paper about it. And as far as my knowledge, is one of the neural network which can give better performances over different kind of crystal graph convolutional neural network. Now, GeoCGNN stands for Geometric Information Enhanced Crystal Graph Neural Network, in a sense that it's like a usual crystal graph neural network, but it's also introduce information about the geometry, and as I said before, also physics a bit. For now, so what is implemented here, I put a GitLab repository developed by Claudio Ronchetti, which I have to give credits for starting this the implementation of this GeoCGNN within IEMAP or IEMAP, and where he studied basically the CGCNN and GeoCGNN, finding better predictions for this. Now, in the literature, if you go, you see that there is this GeoCGNN have better performances. I mean, it's in a sense that it gives much more accurate prediction with respect to other kind graph neural networks that you see in the literature. For example, as we study all this kind of neural networks, which are already really good. This study is done still in the paper of the Chinese group, which introduced this GeoCGNN and finding and basically define this GeoCGNN and find it is better performance. And then also in this paper of Claudio Ronchetti and others, in our group of IEMAP, which also check this and apply this GeoCGNN on for the study of batteries. Okay, so now let's talk to the GeoCGNN in more details. So this is the overall structure. So it looks complicated. You already seen this kind of picture, I guess yesterday in the talk of Sergio Ferlito. Basically how it works is that you take the SciF file which contains information of your crystal. Basically the informations about the atomic positions, about the cell in which you put the unit cell in which you put the atoms of your crystal. So the volume of the cell, the three vectors of the unit cell. And then this is the structure. You have a series of gate convolution layers written here. And then this goes in this output where there is this kind of, it's called pooling. And then you have the prediction of your property P. So P is something which we want to predict. For example, for a material can be, I don't know, formation energy, I don't know, band gap, whatever you are interested in your material. In our case, we will concentrate on particular properties for batteries. I will see later. Okay, so this is the first part. So there is a part of embedding. Basically, so there is the, so as Serena said, basically, if you have your crystal, your material, you map the atoms in your nodes and the chemical bonds in edges. But what does it mean in practice? In practice means that in your atoms, you have the information of the atomic number. So this Zi, and this represent basically is represent your the information of your nodes. So what we do is we take this Zi, we do a one-hot encoding, and which is just map this Zi in like in a vector of 0 and 1s. Then there is this matrix W, which just recites the features, the dimensionality of this vector. So it's not strictly necessary, but we use it. And then we have this variable nu80. This variable represents the node at so the node I at layer 0. Then we'll see that this 0 so will be this label will be the label of the layer. Next. Now there are also other kind of parameters which also take this graph neural network, and so like the distance between two atoms or two nodes, Rij, the volume of the cell, the ABC are so are the vectors of the unit cell. If you don't know what I'm talking about, but it's just that when you take a crystal, you have the information of unit cell, and then you have the atomic position related to this kind of cell, this kind of box. Okay, and then we'll come back. This kind of inputs goes in these boxes, which come back later. This is something which has been introduced by FISNet. I will talk about this later because it's quite peculiar of this GeoCGNN. Now, once we have our nodes, we want to update these nodes. And this is done by this series of gate convolutional layers. This is a picture of this, but this just means you have this formula, which every layer as output you have the node at time t. Okay, no at time, and at layer t+1, give it the node at time t. And this will depend by the node I, of course, and by the sum over all the nodes which are in the neighborhood of the node I in this form. Then this, so it has two outputs, basically this omega here and also new high t+1. This is also the information of at the node I, but this is passed on the next gate convolutional layer So we set several gate convolution layers for having better predictions. I mean, better learning of our graph. And yes, now in this sum, we see that we have a series of factors. This times here means is the Hadamard product. Basically, this element-wise product among vectors. These are 3 vectors in this case. This sigma is a sigmoid function. This G can be some activation function. Already Serena told about this. We use ReLU in this case. And this is the part introduced by GeoCGNN. So if you exclude this, you have just a gate convolution neural network. The novelty in this case is introduce this message passing. So it means that the information of the node J is passed on the node I, but if the nodes is too far apart from a node I, then this shouldn't contribute much. This is something which we know from physics. So the atoms which are closest to the given atom I, they interact more, and then if you go far apart in the distance, then they interact less until they don't interact at all. And in this case, we set a radius. We set a cutoff of 8 angstrom. So after a distance of 8 angstrom, you don't have interaction of the node J with the node I. All this W here are matrices and are learnable parameters. So something which should be tuned for, should be found from during the training stage of the neural network for having a good update of our nodes. Now, let's talk about the attention mask, as I said before. So I want to come back on this point just in this slide. So here we have, this looks maybe complicated. This is a feature introduced by this network FISNet in the GeoCGNN. And basically from the information of the distance among nodes, you get this vector, which is given by the different radial basis functions. And these are, BF stands for radial basis function. This PW stands for plane waves. So also have this vector of given by plane waves. And these vectors are the vectors which are I mean, the W here, this learnable learnable matrices multiply these vectors in order to give this attention mask M. This M is the same of this previous slide here. Yes, so we have this radial basis function because you see these are functions in which if you are far apart from node I, then the node J give less contribution. So for example, a node J which is in position, which has distance 1 angstrom in this case, has high contribution to the update of the node of a given node I. Instead, for example, node J which I don't know has distance 6 angstrom has less contribution until after 8 angstrom you don't have any contribution at all of a given node J on the update of the node I. After this, after you have all the omega for a given node for all the layers, you pass this information in something called pooling. So you get this variables gamma t, which depends by the layer, and this you sum over all the nodes. This basically gives you the information of the graph structure. This represents your graph in a sense. And then here there are still also other learnable matrices. And after you get this variables gamma t, you give in a multi-layer perceptron. Already Serena mentioned this. So it's just a layer with it's just a neural network with a needle layer in it. So, and then you get the prediction of your property P. As I said, P is something which you are interested in general. It can be whatever you want. Now let's talk about the application on batteries. So what's how our P is in in some sense. So for batteries, we are interested. Okay, this is a slide really similar to the one of Francesco, so I don't go in the details of explain what a battery is. But the main point here is to consider that we want to compute with our neural network two properties: formation energy, because as already Francesco mentioned it, so it's something which is related on the stability of a material. And so the lower is, the more stable the material is. And the redox potential, or sometimes in the literature is known as also intercalation potential. And this is a quantity also interesting for us because it also related to the stability and performance of the battery. And we want this value to be higher as possible, but not too high, otherwise the battery is not stable, become not stable. So these are the two quantities for our study that we want to predict. For this, we take our data from the materials project database. This is a database which contains a lot of these SciF files, so the files of the crystal structures. And we have 150,000 materials for study information energy, so quite a lot. Much less for batteries. This kind of data are used for studying redox potential, for predicting redox potential. Here we have just 4,000 batteries. And then we do a comparison of, so which are our goal is to do a comparison of our machine learning prediction with the data which are already in this database. Now, okay, let's briefly talk about some pedagogical stuff. I mean, before going the training, I mean, showing you my plots and so on. So what we do, we do the training. So as Serena said, usually people split your data in three different sets: test, training, and validation. Using the part of training, validation is 80%, the test is 20% of all data. This training plus validation is used for see if the training goes well. In a sense, you have the convergence and your network is really learning the information about the crystals that you have. And then the test is something, the test set is used after the training to check if to check the accuracy of your predictions. So and something really important. And we use the Cray-Cross validations. Cray-Cross validation means splitting this training plus validation set in K subsets, and then one of this used for validation. So it's data which are not used for the training part, but for check if the training goes well. And the union of the others are used for the training, really for doing the training. So for adjusting the parameter, the learnable matrix W's that we saw before. Then one can choose this this validation set over different, I mean, K ways. So one can do K trainings and having an average over your predictions and maybe estimate also the errors. So the goal of the training is to minimize some loss function. In our case, we use the mean square error, so which is just just measure the distance between this Y target. This is the data coming from materials project, and this PW is the prediction coming from our neural network, which depends by W our learnable matrix is W, and also all the learnable parameters. Here for W stands for all the W that we have seen before, actually. And so during the training, one starts with random values of this matrices W, and then we do many steps. In every step, we do tiny modification of this W in order to minimize this loss function. So minimize the distance or the error in the sense, between P and so the prediction and the target. And for this, there are different kind of optimizer for doing this. For example, this SGD, which stands for stochastic gradient descent. And in our case, we use the Adam optimizer. I don't go in details of this because it's long way to it's long to explain all these things. But we use a kind of optimizer to minimize this loss function. Now, these are so what you obtain for our training. So as I said, we are interested in information energy redox potential. As we see, so the mean absolute error, similar to the MAC that we see before, but here this is the sum of the modules of the difference between the energy predicted, here the formation energy predicted by the network minus the energy which comes from the database materials project. And here there are epochs are the steps of our optimizer. We can see in this way, and here in this for the training, this goes down. This is okay. Also for the validation, these have the same path, which is okay. It means that the training goes well. Sometimes this validation goes up. If this is the case, then one can have overfitting. So in a sense, the network is learning a lot from the data for the training, but not from data which are not seen from the net. We use, okay, this is a plot for 300 epochs. As we see, the formation energy is good. I mean, we have a lot of materials here. The dataset is large. For redox potential, still good, but as you see, the scale here is different. So this is kind of worse performance, but the number of data are less. So that can explain this. Maybe not only. So we are investigating on this still. And yes. So now we have the prediction. So we use this 20% of the test set for doing the predictions. And this curve, we have the target, so the data coming from the materials project. Here we have still the prediction of the network. So we have 30,000 SIF file. Here the error bus come from this K-cross validation, which we are using. We use K-5. And then we see that we have good small value for MI and MSE. Also R squared, this is a quantity related to how this data spread on this red line, which should be the optimal behavior. If it's close to 1, then it's okay. If it's far from 1, then it's a problem. It's kind of give you some hints of the accuracy of your predictions. And yes, this is for the formation energy. For the redox potential, we have something similar, but of course the data for the training are less, are just 3,000 batteries for the training, so we can expect a worse scenario in this case. So, but still the data goes in this red line here. So the R-square is less close to 1, but still okay. My MSE are quite ME and MSE are quite bigger. We expect the case of formation energy, and as I said, this is expected. So we have much distance between predictions and the target. So in this regard, we decided to study also the scalability. So if I modify the number of training sample, for example, for the formation energy, since there are a lot of data, how the network performance is. So this is the curve of the training. Here we use the K-cross validation. This is the blue line is the curve of training. The orange is the curve for test. See, we mean so data which are not seen from the network. So we see that from small size of training, as you expect, there is a large difference. So the network is learning a lot from the training, much less. So if you give data which are not seen by the network, then you give worse predictions. And then when you increase the number of data for your training, this two-curve approach each other with some distance, but okay. And so it means that GeoCGNN scales well with the training sample, with the size of the training sample. Now let's go to talk about performance. Since all this training and stuff are done in the on Cresco. Okay, already Simone gave a deep overview of Cresco. In this part, I've been focused on the part of Cresco where there are GPUs, and there are in many parts there are GPUs, not all devoted for doing machine learning trainings. But I try to use some of them. I mean, in this case, almost all of them, which are available on Cresco. So there are some Tesla A100, which are in Cresco 5. Here I put that it's going to be dismissed because I don't know if it will be available in the future. H100, there is also in Cresco 5. There is a Quadro RTX 6000 in a cluster of Cresco. And then Tesla 100, there are a lot of Phoenix Cresco, which is will be interesting to, which is new, is a cluster which is now going to set up, and will be interesting to run all this machine learning prediction also on Cresco as well. And also some are in Cresco 6 and V1 and 2, but with a different purpose. So this is the speed up. So of course we have better performance for H100. This is the training, and so we have a better performance. This of course because H100 is one of the latest GPU released by NVIDIA, so it's quite expected this, and then progressively A100 have worse performance. And this is this is for the evaluation. So when we have the test set, we want to evaluate our prediction, and this is how it performs for different GPUs. So of course, again, H100 one of the best. This is we took 3,000 SciF files for doing this. And as you see, also for different GPUs, also RTX 6000, it just takes a few seconds for doing the evaluations. That's the thing I think it's really impressive. So because there is, if you do with the FT calculations, a prediction of one of these properties, I don't know, formation energy, redox potential, and so on, you just need to study every material by its own, as Francesco shown in his last slide. It took hours, in principle. In this case, just you need to do the training at first, and then you can just evaluate in a few seconds your properties which are interested. And this is why it's really important to go in this direction, and this machine learning direction in this field. And so I come to the conclusions. So we have seen that, okay, there is a code for machine learning in this repository. We have seen that the training performs both well for formation energy and redox potential, and also for redox potential, the prediction are reasonably good, but still, since the data are less, there is a margin of improvement. And for this, what I'm doing now is try to implement further improvements in this direction. One of them is of course doing like transfer learning. It's something which Serena a little bit cited a bit. So use this this fact that we have good prediction for formation energy, and use this for improving also the prediction of redox potential. There are different ways to do this. So we are currently I'm currently working on this. And also possible techniques of the documentation. This is not trivial also, and so just to exploit more the small data set of batteries. And yes, so that's it. thank you very much for your attention. And so if you have questions or no.
Thank you, Marco, for your presentation. Would anyone like to ask a question? So with this presentation, we finish the first session of the morning.